Lowe's, but we're only like the Lowe's garden department for like 5 minutes. So I'm sorry, Gabby. I'm recording, so you can always copy it again later. Okay. I don't understand printers. Costco is, when we were dating, actually, we would go to dinner and we would go to Costco, Lowe's, and Barnes & Noble. And that was pretty much a typical date when we were dating. So we missed Barnes & Noble this time because we were in Menifee, Lake Elsinore area versus Temecula, Marietta. So, yeah. As long as you take the girl to dinner first and don't buy her Costco dinner, then you're good. Okay. So we had a thing, we knew somebody else who was dating around the same time we were before, and we all kind of got married around the same time, and he would take her to Costco for a hot dog for their dates, and we didn't do that. So they would go to the movies, and we never went to the movies. So at least pop for Panera or Jersey Mike's, you know, or Five Guys. Five Guys is good. We eat a lot of Five Guys when we're out because they don't have one in Hemet. If they had one in Hemet, I'd probably need to lose more weight. Okay, here we go. We're going to get going. Pizza's tough though, because you got to make sure it's like, you know, good pizza if you're going to take them out. So you got to go to Milano's, and then, or you got to go to Stadium. Milano's is better than Stadium. Or if you're out of town, if you go to Temecula, there's a place called Felipe's off of Jefferson. That place is pretty good. So.
Bogey pizzas, bomb. Their pizzas are huge.
Yes, they're really good. My husband doesn't like a cheesy pizza. Like, he doesn't like cheese. So it's tough around our house, but my kids do. So my kids and I eat the pizza, and then my husband gets spaghetti. All right, we ready? My goal is to probably skip example 4. We're going to do the best we can on this. This one is a lot better in person and live. I had a whole thing I usually do on the board, and we kind of actually do an experiment kind of thing, but I went with this alternate lesson this year because I just thought this is probably what we could handle at this point. But the idea that we're getting into is we have a couple of, we're going to try to use polynomials to estimate things, okay? If you think about it, for 300 years, mathematicians have been able to compute transcendental value with an alarming degree of accuracy. And what we mean by transcendental, remember, is ease, natural logs. Trig isn't transcendental, but cosine, sine, cosine, estimating those things, they've been able to do without a calculator. Long before calculators were invented, they could estimate those things, okay? So how would they find sine of 0.2 or natural log of 1.05 or the 4th root of e without the convenience of modern calculator? Okay, so that's what we're gonna get into, and that's what Taylor and McLaurin are best used for, is doing some of these estimates. Okay, so if we remember back to last year, which would be topic 4.6. Okay, we didn't call topic 4.6 last year, but we did it last year. Okay, no matter what the topic was called. We did linear approximation of a point at C. All that we mean by that is we've got y minus y1 equals m times x minus x1. Tangent line. Okay, that's all this is tangent line. Okay. So furthermore, we rewrote the point slope version of that line. So just all that's different about this. Okay, so we're gonna basically rewrite what we had here. Okay, so all that's different, and I'm sorry it's like crooked. I was copying and pasting fast, and instead of retyping, I just let it be crooked. We could read it, so I was good with it. Okay. All right, so instead of typing in x sub 1, they put in a c. Okay, so same formula. Instead of putting in y sub 1, they substituted the c into the function. It's still the y value. Okay, and then instead of writing m, they said, hey, that's the slope evaluated at c. Okay. Now, to make it so that we could plug things into it, they just reformatted the equation right here. Okay, so all we did was we took this f of c and brought it to the other side by adding it. And then we replaced y with L of x, which means L for line, probably. It's a linear approximation. Okay, so because this linear approximation is a first degree polynomial, we're going to name it p sub 1 of x. So all they did in the next line is, because this is what we had last year, supposedly, we just mostly use this. Okay, but that's officially the way we should have probably formatted it. So instead of naming it L of X, we're going to name it P sub 1 of X. It's the exact same thing. It's the equation of a line in point slope form. That's all that is. Okay. So it has some important properties. And again, I'm going behind the conceptual of this first, and then we will get into the nitty-gritty of how to do the calculation. Okay. So this polynomial has some important features. It matches the function f at a value x equals c. So if we have this picture here, okay, so see this picture down here, okay? This is the function, the blue is the function, the red is the line, okay? It matches in one point, okay? So that's one feature. So we know that the y value is the same somewhere. And then at that value c, the slope is the same. So it matches the slope. So our slope at that point and our equation of that, and our y value are the same, okay? So we could use it to estimate the value of the point, but it's a little bit tougher when we need to estimate the curve, okay? And try to get a good approximation on the curve. So the linear approximations don't always work well, so the graph of the f has a great deal of curvature near c, okay? So we can't, since this curves quite a bit at c, we're not getting a good estimate, okay, of the value. To fix this problem, we can create a quadratic approximating the polynomial by adding one new term to the linear polynomial. So we're going to make the notation on it is going to be our p sub 2, meaning it's the second degree polynomial. Okay, it would look like this. So all we did is we added this guy here. Okay, we don't the coefficient right now is arbitrary. We don't know what it is yet. Okay. And we will find out eventually as we go through the lesson. We will figure that out. I'm trying to find my notes here. And then we'll notice it's x minus c. So it's the same notation here. And instead of making it to the first power, we are squaring it. I'm making sure I know what to fill in here. Okay. So notice that we need to find a value of the coefficient of a. To determine a and to ensure that p sub 2 of x, at what something else is not supposed to be. Determine and to ensure that p sub 2 of x is a good, I don't know why the word at is in there. The word at shouldn't be there. Is a good approximation for f near the point c. We require that p sub 2 of x agree with the f in value, so that means y, okay, slope, and concavity. We want it to have that same concavity. So in other words, p sub 2 of x must satisfy the conditions. So basically, it has to have the same y value. So this means same y. It must have the same slope. And this all means that it must have the same concavity. Okay, that's all of that funky notation means. I'm not going to go through with all the derivatives and all the meaning of it and figuring it all out, but that's what all that means. Okay. All right. So do you see how the green here matches the curve a lot better than the red does? So I would get a better estimate of that, whatever that blue curve is, with the green function, which is my polynomial sub 2. Okay, so I'm going to have you help me a little bit more now that I've got through that piece of explanation. Okay, so I'm going to start asking some questions in the chat. Okay, so hopefully you're back awake and paying attention. So we're going to find the linear approximation and the quadratic approximation. So I am going to go back in and I'm going to use that function that we came up with. So I'm only writing it down because I don't have it on this screen already. Plus f prime of c times x minus c. Okay. So they gave me the function as natural log of x, and they're telling me to approximate it at x equals 1. So this is the c value. Okay. The first thing we're going to do is we're going to plug the c value in. Okay. So I am going to say, and so we're using this to approximate the natural log of x. Okay. So actually I should use approximately symbols. P sub 1 of x. Okay, I see what they're doing. equals, okay, the natural log of c, because that's our function at c, right? So the function is natural log evaluated at c, plus, okay, here comes my first question. What's the derivative of natural log of x? Tell me in the chat. Derivative natural log of x. Let me know you are still awake and here. I don't have quite all of you yet. Make sure you're answering, because again, I'm giving you points for being present in the chat throughout the lesson. Even if Mrs. Ballard's really boring today, you have to be present in the chat. Sorry. This is a dry one. All right, so 1 over x, okay? And then we're just going to leave x minus c alone, right? That's what it says, because all I did was recreate this formula for our specific situation, okay? Let's see. Yep. Now I'm going to go ahead and we're going to plug the c value in. So I am going to find, I don't know why he didn't plug in. So we're going to approximate p sub 1 of 1 by, oh, I know why. We have to finish filling in because the x value isn't. So this x value is not the c value, okay? What they're talking about is to estimate x, we have to plug our c's in here. And I have a typo right here. This shouldn't have been x, it should have been c, because we have to evaluate it at c, okay? Because it said evaluated at c. So I'm going to plug my c value in. What's my c value right now, everybody? Put that in the chat for me. What's my c value? That's what confused you, is the c value. The c value, oh, so because it was x equals, and then we plug a c in there. The c is being represented, I know, and it is kind of tricky, okay? So we're going to approximate it x equals 1, but we're going to use that as the c value, okay? And I know that's weird. That's just something you got to get used to. 1 over 1 times x minus 1. All right, now I need to figure out what is going on at each of these. Oh, I need to calculate this, okay? Because we're just doing this in terms of x. We're doing p sub 1 of x, because we don't have anything to plug in for the x and estimate yet. That's in part C, okay? So what's the natural log of 1, everybody? What's the natural log of 1? You're slowly getting there today. Okay. It is in fact 0. And then we would just have 1 times x minus 1, which would be x minus 1. So my polynomial, my first degree polynomial, and I probably took 3 more lines than I needed, is x plus 1. So in order to estimate this natural log, if I was going to use a linear approximation, I would use x plus 1. Okay? All right, we're going to now find the quadratic approximation, and then we're going to look at those for a specific x value. Okay, I'm waiting. I'm just going to slide my screen a little bit.
Ms. Ballard?
Yep, go ahead, Natalie.
Is that a subscript of 1 or 2? Or like
It's a 1.
Okay.
I tried to write over the top of it because it looked like a 2. It's a 1. Okay. The good news is I don't have to write down my formula, because my formula for this one is right here. Okay, they gave it to me on the same page. Okay. We didn't go through that, did we? Oh, okay. So the a value that we plug in here, okay, and that's the part that I missed explaining, changing pages there. Subtracting 1. Yes, I should be subtracting 1. Thank you for the catch, ladies. It should be x minus 1. Everybody catch my boo-boo? Okay. All right. So what we were actually getting here in the pattern that we have is that you take the derivative, okay, and then the next one is the second derivative, and we happen to divide it by 2. That was, I didn't explain the calculation, but when they did to match the curvature, that's what ends up happening. It ends up being 1/2 times the second derivative. And again, you don't need to understand completely where that came from to do the problem. Okay, so we're going to use this formula that we're going to assume was given to us. Okay, so I'm going to approximate the natural log of x again. I'm going to kind of write it out in terms of C for our specific problem. And this would be the P sub 2. So P sub 2 of X. This is approximately, okay? So, and I'm going to plug in my C's first, and then I'm going to plug in my 1's, my specific to the problem. Okay, so it would be the natural log of C plus, you already told me the first derivative, because that's what has to go next. It says first derivative evaluated at C. So we know that that would be 1 over X, which is 1 over C, times X minus C. And then plus, okay, so if my first derivative is 1 over X, or X to the negative 1, what's my second derivative? This is first derivative. What do you guys think? What's the second derivative? It's not natural log of X. Remember derivative, we take the number, we move it to the front. Natalie is saying negative X to the negative 2, Lorenzo 1 over X squared. Okay, so negative X, I subtract 1, negative 2 equals negative 1 over X squared. So this would be negative 1 over, instead of X, we're using C squared. The times the 1/2 is the way I'm going to write it for that, divided by 2, X minus C squared. Okay. And again, what am I going to plug in for C, everybody? So what's going to get plugged in for C? I want to make sure we're all still awake. Good morning, David. I just noticed you popped in. Okay, so we're going to plug in the 1. So this is still my polynomial of second degree. So natural log of 1 plus 1 over 1 X minus C plus negative 1 over 1 squared is 1 times 1/2 times X minus 1 squared. I'm going to clean that up. What was the natural log of 1 again? Good, good, good. 0. Okay, so I'm not even going to write it down this time. Okay, 0. Okay, because then I'd have to write less lines of work. What did I miss? I missed plugging in a 1 for this C, didn't I? So minus 1. So we did, and then this is just going to be X minus 1. And then this is going to be minus 1/2 X minus 1 squared. It doesn't hurt to put those parentheses. You might see things better if you leave those parentheses on it. Okay, so if I'm going to estimate using a quadratic estimation, I'm going to use that polynomial. Okay. So here's where we're going to go, and we're only going to use the calculator for maybe some calculation purposes. Okay. I am going to estimate both with a linear and with a quadratic. So I'm going to do my linear estimate and my quadratic estimate. So we're going to estimate natural log of 1.05, and then we're going to do this into P sub 1. And we end up with 1.05 minus 1, which is 0.05. Don't simplify it. No. You'll see why here in a second. You're going to be, if you simplified it, you would be not liking it, okay? Especially if you didn't have a calculator on this piece, which we do, but if you didn't, you would not be liking life, okay? All right, so I'm going to do my quadratic estimate. So my same number, same thing that we're estimating, we're just using the quadratic polynomial to estimate, equals 1.05 minus 1 minus 1/2 times 1.05 minus 1 squared, which means I've got 0.05 minus 1/2 times 0.05 squared. Okay, I'm going to put that into my calculator because at this point, I'm not going to let my brain try to do that. So I'm on my scratch pad. 0.05 minus, and remember, right now we're developing the concept. Okay, and you were trying to see how this thing works and why it works. It was 0.05, right? Not just 0.5. Let's see. Go back. 0.05. Okay, 0.05 and then squared. 0.4875. So look at my estimate probably got better. Definitely more decimal point accuracy. How much of a curvature does there have to be to use a quadratic approximation? we're going to find here in a minute that the more we have, the better our approximation is. So we're going to compare the approximations in just a minute, Lorenzo. So bear with me, okay? All right, so this one was 0.04875. All right, so let's see how good we did. We all have the power of technology, unlike the mathematicians 300 years ago, right? Newton didn't have this. Leibniz didn't have the power of technology, but we do. So let's actually put this in our calculator and see what happens. So if I do the natural log, so control natural log of 1.05. So think about what we just did there, you guys. We just used a polynomial to estimate the natural log of 1.05. And look at how close we got. Did we do pretty good? Like we were within one, that's what, tenths, hundredths, thousandths, 10,000ths? We were within one or a couple of 2 10,000ths of being correct by using a polynomial estimate. It's pretty darn good, okay? So how do these approximations compare to the actual value? Which one is better for our approximation? Was it linear or quadratic better? Yeah, the quadratic was better. Do you think I could get closer? What would I do to get closer? What do you guys think? What would we do to get closer? Oh. Could I get closer than a cubic, do you think? Do you think I could keep expanding that polynomial more and more and more and get it closer and closer and closer, maybe? So we can extend the idea of linear and quadratic, okay, to higher degrees polynomial, and we will do a better job of approximating functions, okay? The one I usually do is I usually do sine or cosine, and we look at the pattern, and we see that we can estimate sine and cosine with a polynomial. It's pretty cool. So the good news is yes, we can do it with we can do this with polynomials, okay? So we're going to kind of summarize what we did here, okay? So we observe that P sub 1 of x equals f of c plus f prime of c times x minus c, and that P sub 2 of x equals f of c plus f prime of c times x minus c plus a times x minus c squared. So it's only logical that our next step is put another coefficient in front and make the x minus c cubed, okay? After that, put another coefficient in front, x minus c to the 4th, okay? And then put another coefficient in front, x minus c to the 5th. Okay, so I can keep going, however many they ask me to do, okay? It remains important to satisfy the 4 conditions. So basically, what are the conditions that have to be met, okay? So because P sub 3 of x is built using P sub 2 of x, the first 3 conditions above are met. So basically, my y is the same, my slope is the same, my curvature is the same. We need to get the jerk, right? The third derivative is the jerk. That needs to get the same, okay? The first 3 conditions above are met. The last condition, P triple prime sub 3 of c equals the third derivative evaluated at c, is used to find the coefficient of b. So to find those coefficients, part of it is finding the derivative. And hopefully you're noticing that for the second, I needed the second derivative, right? And the exponent was a 2, okay? I need the third derivative, and the exponent is a 3. Hopefully you're starting to see a little bit of a pattern. On this one, I had the first derivative, right? And the exponent was a 1. So those things match, okay? By the time we reach the third derivative of P sub 3 of x, we notice that P sub 3 equals f prime of c plus 2a x minus c plus 3b x minus c squared. The second derivative is 2a plus 3 times 2b x times x minus c. And then the third derivative equals 3 times 2 times b, which is equivalent to 3 factorial. So now we're introducing how do we get the rest of that coefficient, okay? So really what's going on is when I start taking derivatives of these things, right? Think about what's going on. This number keeps popping in front, right? And every time I pop that in front, I end up multiplying by the number, and it was the previous number was just one less, right? Or one more. Okay, so I'm not super worried about you understanding this. This is a lot of stuff. We're going to learn how to crank these out, okay? So this is all the mathematics behind how do we get these coefficients that go in front of x minus c. Okay, so I'm going to teach you how to do that. All right, I'm going to show you the pattern. That's what Taylor is about. Okay, I'm not worried about you understanding the conceptual there. Okay, so can we keep going? So the way that we get these coefficients is we take whatever the derivative that matches over the factorial of the number of the term. Okay, so look at the pattern. So let's look at the pattern that's in here. Okay, so we have to find the nth degree Taylor polynomial. Okay, and it's always going to be centered somewhere. Remember we said that, hey, we've got, we had a c value. It's always going to be centered at the c value. Okay, so the last one, it was 1. So we put 1 in for the c. So look at the pattern. I start with, really this is like saying x minus c to the 0 power divided by 0 factorial, right? This one is saying I'm going to take the first derivative. I'm going to have x minus c to the first over 1 factorial. So this is my 0 term, my first term, my second term. So look at what happens with the second term. To set up the Taylor polynomial, you take the second derivative, you divide by 2 factorial, you do x minus c squared. So my third term, okay, let's do a couple term patterns and then hopefully you'll see it, okay? So f triple prime, because it's the third term, evaluated at c, over 3 factorial times x minus c to the third. Okay, let's look at what the fourth term would look like. So the fourth term, what derivative do I need? So if I'm at third term needs third derivative, but the fourth term needs what? I'm waiting, I want to make sure we're all there. Okay, so we need the fourth derivative right now, okay, which remember we write like with that. Fourth derivative evaluated at c, okay. We're going to divide. What are we going to divide by? I want to make sure we're seeing the pattern. Okay, we divide by 4 factorial, x minus c to the 4th power, dot, dot, dot. Okay, is the pattern making more sense? Can you put a smiley face in the chat if the pattern's making more sense now? Gabby, that's the same smiley face that Nate put in the chat yesterday. That's really weird. I told him it wasn't a smiley face. It really was. Like, what is wrong with that? Okay, so look at in the nth term spot. So basically, I keep that pattern going. I take the nth derivative, I evaluate it at c, I divide by n factorial, I go to the nth power. Okay, so that's a Taylor. So Taylor invented this thing, or at least he's credited with it. Okay, then Maclaurin comes along and says, hey, I can do you one better. All right, if my c value is 0, okay, Yes, Taylor's expanding the polynomial, and we're going to use that polynomial. We can use that polynomial to estimate a transcendental function. Okay, that's what's really going on here. Okay, they were coming up with a way to estimate what natural log was without having to plug in weird small tiny decimals into natural log. Okay, because again, no calculators. Okay, so Maclaurin comes along and says, hey, I can do you one better. When you don't have this, when you're centered at 0, guess what? I don't need the x minus c part. I just use x. So the only difference between Taylor and Maclaurin, it's the same idea, except that it's x instead of x minus c, and instead of c, it's 0 everywhere. Okay. Sometimes they will say on the AP test, a Taylor polynomial centered at 0, which just means you're doing a Maclaurin. You don't need to super remember Maclaurin Taylor because Maclaurin is Taylor. Okay, it's just the C is 0. Okay, so as long as you understand the pattern, we're good. All right, I don't know what I was thinking when I copied and pasted this in. Okay, because I give you like no space there and a little chunk there. Okay, I would recommend going to the second page and writing in the little chunk of space there for what we're going to do next. I'm going to write it off to the right side because my handwriting is going to get too big for the space. Okay, it's not a ton of stuff that we got to write, but there's enough there that we're going to draw a table. So I'm going to show you how I set these up. So it says Maclaurin polynomial. We're going to write a Maclaurin polynomial for sine of x. Find the 7th degree. So 7th degree Taylor Maclaurin polynomial. So that means we're centered at 0. That's it. So that means our c is equal to 0 when you see the word Maclaurin. Okay. P sub 7 of x for f of x equals sine x. Okay. So I am going to start. If I need the 7th degree Taylor polynomial or Maclaurin polynomial, how many derivatives do I have to take? I'm waiting. I want to make sure I hear from everybody. You don't have to be a math. You can still be a math major and not like Taylor and Maclaurin. It's not my favorite stuff in the world. You haven't even explored like number theory and cryptography. You'd like that. All right. And linear algebra is amazing, especially if you're a computer person. Linear algebra is awesome. All right. So I highly recommend those classes. Okay. Okay, let's keep going. So what I'm going to draw here is I'm going to draw a little table for myself. Okay. And this is the way that I set this up. Not every teacher will do this the same way. Okay. So this is the Mrs. Ballard's take on this. All right. This helps me keep my work organized. I like to do all my derivatives and evaluate all my derivatives in a table, and then I just write out my polynomial. Okay. So I'm gonna just use the patterns that we saw in this green box. Okay. So this is we're gonna call this f and derivatives. Okay, and then this is where we're gonna evaluate at 0. So c equals 0. We're gonna plug 0 into all of them. Okay. All right. So somebody has to be able to be smart enough to program the computers and the computer graphics and understand the linear algebra, or we wouldn't be doing anything that we're doing right now. So somebody has to be able to do it. So it's a good job. Okay, so f is sine of x. So this is f equals sine of x. And I'm being pretty informal about this. So what's the derivative of sine, everybody? It's been a while. What's the derivative of sine? Cosine x. Cosine x. Perfect. Okay, what's the derivative of cosine, everybody? All right, negative sine x. All right, derivative of negative sine x. Are we seeing a pattern? Negative cosine x. And then I do the fourth derivative is the derivative of negative cosine, which should be back to sine x. And I'm going to keep going until I hit 7th derivative. Okay. So this would be cosine x sixth derivative is going to be negative sine x, and seventh derivative is going to be negative cosine x. Okay, I'm going to squeeze that in a bit, move this over so you can see my work. Okay, so let's get out your friend and mine, the unit circle. That's all I need. Okay, so I don't even think I need this part. I just need this part because we're only evaluating at 0. So what is the sine of 0? It's only 2 choices, right? Okay, it is in fact 0. Good job. Okay, the cosine of 0 is what? 1. Nice. Okay, and then we've got the negative sine of 0 is still going to be 0. Negative cosine of 0 would be negative 1. Hopefully you're seeing the pattern. Okay. Sine of 0 again would be 0. Cosine of 0 would be 1. Negative sine of 0 is 0. And negative cosine of 0 equals negative 1. So what you're hopefully seeing, okay, is that these are going to be the coefficients. So these are your coefficients. That's supposed to be an E. So my first period yesterday, we were learning natural logs. And I wrote it like this, right? Past few years, there's been a weird trend where I'd be getting this on the tests instead of an L like this, right? Guess what letter they gave me in the chat yesterday? Instead of natural log, guess what letter they get instead of a 1? They didn't give me an 8. They told me it was E, E-N. Because it looked like an E. Anyways, I digress. That was what I thought about when I was writing the EM coefficients. Okay, so those are your coefficients in the formula that are going to go in for f of, because this is Maclaurin, right? It's going to go in for f of 0, f prime of 0, f double prime of 0, and so on. Okay? All right, and I'm going to write it out with all the zeros in there so you see the pattern, and then we will write a simplified version. Okay, so because we're doing 7th, I call it the polynomial of 7th degree, so p sub 7 of x. Okay, the first thing I'm supposed to put into the formula, remember, is just f of 0. So I'm going to put in 0. Then I put in f prime of 0. So f prime of 0 is 1 divided by 1 factorial times x minus, or just x, because we're not doing whatchamacallit. We don't have a c value. So x to the first. I'm being overemphasizing where everything is being plugged in. Okay. Then we're going to do, so that we've done this one, we've done this one. We're going to do second derivative now. So second derivative was 0 divided by 2 factorial x, I keep wanting to draw parentheses, x squared. Okay. Plus my coefficient, we've done this one, we're on this one now. So plus negative 1 over 3 factorial times x cubed. See how I tried to draw my parentheses again? All right. Plus 0 over 4 factorial x to the 4th. Plus 1 over 5 factorial x to the 5th. I didn't write small enough. I'll write the last two in a different color. Plus 0 over 6 factorial x to the 6th. Plus, I apologize for my poor placement there. Negative 1 over 7 factorial x to the 7th. That's a 6th power there. Let me get it so you can see it. 6th power. I'm going to scroll up. Okay. And I know we're at time. We're going to keep going because we're going to finish because I don't have this videoed for you. So we're going to keep going, and what we're going to skip example 4. Okay. It's going to go faster on the next one. The first term is 0. It's always just your function evaluated at 0 or your function evaluated at c, your original function. Okay. All right, let's clean that up because we need to, yes, so sine of 0, correct, Gabby, in this case. All right. So what I'm going to do now is I'm going to clean that up. I'm going to get rid of all my zeros and I'm going to multiply out all my factorials. So p sub 7 of x equals, this first thing, that 0 is going to go away. I would just get x. This one's going to zero out. So this one's going to be minus 1 over 3 factorial is 6x cubed. And then this would be, oh no, the 0 would go away, plus 1 over 5 factorial. 5 factorial is that 120? 120x to the 5th. The 6 goes away. So minus 1 over 7 factorial is 5,040 x to the 7th. Done. Much easier now, right? Than trying to explain the conceptual. Okay. All right. And I'm sorry, my conceptual explanation was not great. Much better when I have my whiteboard and I can write across the whole whiteboard. It depends on where your Calc 2 professor goes. If you're going to understand how to do probably they're going to test you on the polynomial more than they're going to test you on the theory, but I don't know. A lot of times in college in a math class, this professor will talk about the conceptual in class, and then you need to go to office hours or the TA section of it and make sure you understand how to process the problems. That's why YouTube is also great. Okay, this is Calc 2, yes. Okay, all right. That's why you took this class, right? Because when you go to college, it's like them speaking a foreign language sometimes, okay? And then they also sometimes have an accent you don't understand, all right? So that's where, and it makes it more difficult, all right? You can still watch, you all have access to my YouTube videos, okay? But I don't do Calc 3, okay? So I only do up to Calc 2 part, and I don't know that we hit all of Calc 2. We get a good chunk of it though, okay? All right. So there's a guy, write this guy down, okay? He's good for, I used him a lot when I first started. Patrick JMT, find his YouTube channel, okay? He's really good, all right, and explained it really well. And he does above Calc 2, okay? No. It's been many moons since I have done Calc 3, like over 20 years. So actually, it's probably been about 23 years since I've done Calc 3. So I did it in my sophomore year of college. No, freshman year of college. Maybe it was freshman year. I can't remember. Okay, good refresher for me. Thanks. I have lots of extra time on my hands, don't I? Calc 57. No. Okay. All right. So all I'm going to do now is I'm going to use this guy here to estimate sine of 0.2. So p sub 7 of 0.2, which would be sine of 0.2, really. I should really write that. So basically what they're saying is, hey, I'm going to plug 0.2 in there, minus 1/6 times 0.2 cubed, plus 120 times 0.2 to the 5th, minus 1 over 5,040 times 0.2 to the 7th. When I actually use my calculator to do that calculation, this is what I got, okay? So we're going to assume you can push the buttons on your calculator. All right. So what do you notice? Let's talk about this. So what do you notice about the degree of each term? So looking at this guy right here, what do you notice about the degrees of each one of the terms? I think Gabby typed it before. It's not because... Okay, Gabby, we didn't use C's on this one because it was McLaurin. Technically, our C was 0. So we used them, but they were zeros, okay? Gabby's right, they're odd, okay? Hopefully we all caught that. So if so sine is odd. Sine has odd degrees. What do you think cosine's going to have? Oh, maybe cosine would have even degrees. Do you know how we have even and odd functions? And we told you, hey, you have to plug this thing in like negative x in to decide if it's even or odd. Well, look at what we've always said, hey, sine is an odd function and cosine is an even function. And we're like, okay, that seems kind of random. Well, here it is, right? When I estimate it with a polynomial, sine is an odd function and cosine is an even function, because we would get the even degrees on when we write out the cosines, okay? So remember, even functions have even degrees, odd functions have odd degrees, okay? What we have told you all along is that when you substitute in negative x into a function, if you get the original function back, that it is even. And when you substitute a negative x in, if you get the negative of the original function in, it's odd. So that's what our test usually is, to determine even and odd, if it's not obvious. So if it's like a log or a cosine or a sine, okay? If it is, but now we know that, look, we can estimate sine with an odd degree polynomial, so we know that it has to be an odd function, whereas cosine has to be an even function, okay? All right, let's move on this one here. I'm going to do example 3, and that's going to be it. And then you guys have time to work on the assignment. Okay, we're going to skip example 4 because I think it's beyond where we need to take this. Okay. The good news is this one's in a table, so we don't have to do all the like massive calculations. Okay. I made it a Delta Math assignment. They're going to have you do the calculations like we did in the table. Okay, so you're going to have to do that. So this one is just, do we understand the concept of Taylor and how to crank that out? Okay. So they told us that we're going to go, let's see. F is differentiable for all orders of n, has the following derivative values when x equals 1. So what's our C value if x is supposed to equal 1? They might be more complicated on the homework, yes. I'm sorry. But at least it self-checks. All right, it looks like the 4 people I for sure still have paying attention. Oh, 5 people, 6 people. All right, 7 people, 8 people. Okay, we all say that it's a 1. Perfect. All right, so we know that our C is a 1. I need to find third degree, so I need to go out to 3 derivatives, which they happen to list in the chart. So I'm going to find polynomial sub 3 of x. So the first thing I do is just the function, the original function evaluated at 1, which is just 2. Okay. Then I need the derivative divided by 1 factorial times x minus the C value, which is 1. Do I really need the 1 factorial? No, I'm trying to help you establish a pattern right now. Okay. Plus the coefficient of the second derivative, so 1, divided by 2 factorial times x minus 1 squared. Plus the coefficient of the third derivative, so negative 6, divided by 3 factorial times x minus 1 cubed. That wasn't so bad, was it? And think about this. If this is non-calculator on the AP test, this goes really well with all the other table problems. Okay, so really easy for them to give this to you in a table. And I want to say the BC test last year, which is not the same thing you're doing this year. Okay, BC test last year, I think probably embedded it in there. Okay. Yes, they will tell you Taylor or Maclaurin, but the fancy thing they like to do with it is they like to say a Taylor centered at C equals 0, which just means Maclaurin. That might be a good thing, which you would know because you put 0 in there. Okay. But yes, they will always tell you Taylor and Maclaurin. Okay. There's one other thing we're going to talk about, which is power series. So that's coming. They may use those words, but we'll take that step when we're ready. Right now, it's Taylor Maclaurin. Okay. And right now we're just doing polynomial. We're going to swap this into a series soon. Okay. It will get there, Gabby. Okay. But again, you have half the battle right now. Okay. It really is kind of a series right now. We just don't have it going off to infinity. Okay. All right. So we've got 2. I'm just going to make it prettier. Minus 3 times x minus 1. 2 factorial is 2 times x minus 1 squared. Let's see. Negative 6, if I thought about this, negative 6 over 3 factorial. Aren't these guys going to cancel and just be negative 1x minus 1 cubed? Or I could just have done negative x minus 1 cubed. Okay, it's perfectly acceptable to leave it like that. Okay, so go ahead, you can leave it like that. In fact, you shouldn't go further than that on the test. Is it a plus sign? Did I mess up?
Like
Should be a minus sign.
between -3, x minus 1, there should be a plus sign right there.
Thank you. Thank you. Okay, that's what I have there for today. Okay, I haven't got official confirmation from the site yet. How do you know when to plug a value in? Because they ask us to use it to approximate something. Does that make sense, Gabby? Okay, so they have to be specific. Hey, use this to approximate, use this to estimate. Okay, and then you know to plug it in. A lot of times there will probably be one where you just have to write out the Taylor polynomial. Yes, I can scroll up. How far? Top. So like there. All right. So something else we're waiting for, the top of the bottom. Well, I don't know what you meant. You have to be specific. I think that's my bottom page, right? Yeah. And we're going to skip 4. So you can cross out 4. Okay. Something else you guys should know. They haven't officially told me this decision yet, but this is what I have heard. Okay. We're going to probably use the second testing window, which is May 24th for our test, which is pencil and paper, which will have to be on campus. Okay. So we will all be on campus at least one day together. All right. You're not getting a 2, Gabby. We haven't even started reviewing yet. Natalie, you're not getting a 1. Think positively. Okay, you'll be fine. I don't know anything about graduation. They haven't said anything. Okay, no, we are not positive we will get a 1. We are positive we're going to work hard and not be lazy. Okay, and we're going to work a little bit more. Okay, I need you guys to work for me for a couple more months. Okay, so the other couple things that are coming up is this Saturday, which is what, March 6th? Is that right? March 6th, we have an AP readiness. Go to it. Okay. And then next Saturday, March 13th. Okay. We are going to do, get this, are you ready? It's super exciting. You ready for it? All right. So we're going to do Hemet Unified, AP Calculus, multiple choice March Madness. Okay. So we will be together. It's on a Saturday. We're going to go 10 to noon because my AB, the calculus class, thought that was better. It's going to be AB and BC mixed, so it'll be a little bit more AB focused, but let's be honest, you all probably need it. And we haven't examined multiple choice in a while, but it's going to be all 4 Hemet Unified schools together. Okay. I'm sorry it's your day of your birthday party, but it's only 2 hours. Let somebody else do the work for your party. Okay. All right. So it's only 2 hours. Come for some of it, part of it, all of it. There were supposed to be packets for you to pick up. I don't think they've arrived at school yet. I haven't heard anything about it yet. But it's going to be, I'm going to do a little bit of teaching. Mrs. DeWitt's going to do a little bit of teaching. Mr. Keys is going to do a little bit of teaching. So you get to hear it from another perspective. Okay. And I will be there the whole time. I don't know exactly how we're going to set it up yet, but come, have fun. Okay. Represent Talkwitz. Okay. And I will throw a little bit of extra credit at it. Okay. So if you show up for those 2 hours. Okay. All right. And then we're going to do a couple more of these, the Hemet Unified ones. I want to say there's only one more AP readiness. Okay. We'll do a couple more of these. We have, I think, 1 or 2 scheduled in April. We might have a couple over spring break. I can't remember. And then we've got like 3 scheduled in May. Okay. So we're getting you ready and the idea is it's kind of the Saturday review, but we're only doing 2 hours at a crack because I think that 2 hours online is plenty. Okay. All right. It's a lot of fun. Let's do the joke of the day. Okay. Calculus on the weekends is the best, isn't it? And eventually the upside of that, of us splitting it up with the other teachers, is we can probably get some BC time in too. So we can split and sometimes go with, Mrs. DeWitt for BC, sometimes come with me for BC. Okay. The other thing is that sometimes it's fun to watch the teachers teach together, okay? I did that last year with Mrs. Rondeau, and it went really well. It was much more entertaining than just watching me by myself. All right. Oh, good. I get to log in. It didn't even come up for you guys. I had to log out of everything yesterday, and, like, reset the cache. So everything I have to log in like it's the first time now. It's a little ridiculous. Okay, here we go. All right, let me redo this. Dismiss, present now, tab. I don't hear him out there right now. In fact, I wonder what's going on. Okay, here he comes.
Okay, it's time for the funny joke. So yeah, what time do you eat at night? Pineapples.
I think it's supposed to be because it has the word nap in it.
Oh, I'll be here all week because I live here.
And the toy bomb went off behind him. You guys have better birthdays than my daughter. Do you want to know what happened to poor Ellie? So, the year Ellie was born, I was the testing coordinator. In other words, I was one of the people who was in charge of running testing at West Valley. She was born on the second day of state testing. So guess what she gets to do every year on her birthday? All right. For Taylor's series, you're going to follow the pattern, and it's going to tell you how far to expand it, Lorenzo. Okay, we'll always tell you, I want a degree 3, I want a degree 4, I want a degree 8. Okay, so it will be very specific on that. All right. Okay, I've kept you guys way too long. Go work on the homework, or actually take a break and then go work on the homework, get it done. It shouldn't be that bad. And if you need some more explanation or how they do it, I don't know if there's videos for this. There might not be. So you might have to email me or text me and ask. Okay. I will be on here. I'm going to get up and walk around for a few minutes because I need to be away from the machine for a few minutes, but I will be here. Okay. If you need it, if you've got questions. All right. Have a great day. Bye, Natalie. Bye, everybody. You're welcome. Bye, Gabby.
Miss Ballard?
Yes, David.
So with these Taylor polynomials, like the first thing we have to do, we have to start with, so with all polynomials, it has to satisfy the 4 conditions, right? For each type.
Yes, but we're not going to be worried about that conceptual piece. I want you to follow the pattern. So you figure out what you're estimating your polynomial to. If you're estimating to the 3rd degree, the 4th degree, 5th degree, 7th degree. Okay, and you take that many derivatives.
So you take that many derivatives and then
plug your C value into all of them.
And then that's all we're doing for now?
That's all you're doing for now, yep. And then, then you have to write out your polynomial pattern from there.
Yeah.
Okay. Got it?
Think so.
Okay, go practice. Don't wait.
Right, yeah, I already have Delta Math pulled up.
Okay, good. Go do it.